So hello everyone. I go by DCBuilder on Twitter, DCBuild3R on Twitter, or X, if you will. And so today I'm going to be giving a little talk about zkML and sort of deep diving into a little bit of the approaches that different teams are sort of going with when talking about zkML. So it's not going to be as technical as all the other ones. It's mostly talking about one of the specific use cases of zk. So what is zkML, or zero knowledge machine learning? So zero knowledge machine learning is essentially creating proofs, zk proofs, of the inference step of machine learning models. In this case, you can think that machine learning model can be a function, right, as any other function, and you have some input, you're feeding it through this function. This function in this case can be either like a classifier or aggressor. In machine learning, there's this there's different use cases for machine learning, right? Like you can, for example, classify an image, whether it's an image of a dog or a cat. You can, for example, predict some output based on some lots and lots of data. So let's say like I want to predict the cost of a house in some neighborhood based on some input data that can be like square footage or like location, some amenities, et cetera, et cetera. And this model can give you an output predicting like what is the fair price of this according to some historical data. So why would we ever want to create a proof of like this inference step? So what zk provides us is this verifiability of execution, right? So I'm able to prove that some function or some program ran correctly, and I can also optionally hide parts of said computation via the zero knowledge property of circuits. So that's the gist of what we're doing. So also another note is we're only doing proof of inference. In machine learning, there's mostly two types of operations you can do. You can either do a training of a machine learning model or program. In this case, you're sort of putting some lots and lots of historical data into this sort of training method, which generates this function that then becomes the model. Or you can just have this trained model that has already like gone through all this expensive training, and you can just do inference, right? Like I feed it some input and I have some output from it. So the reason why we're only doing proofs of the inference step is that training is really computationally expensive. Traditionally, like it takes several months on really expensive hardware, right? Like you have all these, for example, in the context of large language models, I'm sure all of you have heard of GPT or ChatGPT or Llama or all these other large language models. They take many, many months on really like powerful hardware. And if you want to do that inside of a zero knowledge proof, it's very infeasible. So if you wanted to do something within zk, the only thing that's feasible at the moment and that even like has some use is inference. So today I'm going to be talking about sort of more of like the technical approaches that teams have had in the zkML space. So there's different approaches in this case. I list a few of them here. So one of them is, first of all, I'm going to introduce what this ONNX keyword is. It stands for Open Neural Network Exchange. It's essentially a format to represent these machine learning computations. It's like a standard API, if you will, like different machine learning frameworks when they're implementing machine learning operations, so that you can go seamlessly from one to another and export and import, like serialize, deserialize, if you will. They sort of output this ONNX format. So if people want to like build a machine learning model, let's say using TensorFlow or PyTorch, which are very popular frameworks, they can always export them to this ONNX format. And so when, for example, the first approach is like when you're going from ONNX to a zero knowledge circuit via a compiler, what you're doing is you're converting this ONNX format to a zero knowledge circuit in a standardized way. So this approach was taken by the zConduit team, led by Jason Morton, Alexander Komuto, and a few other folks. And what they're doing is that they build a compiler that essentially takes an ONNX file exported from some machine learning framework, and it outputs a Halo 2 fork, a Halo 2 circuit out of it. They're using the Halo 2 fork from the privacy scaling explorations group, and the interface is fairly simple. It's like a CLI tool. I'm going to show a demo a little bit later. Another approach that some folks are taking is that they're actually just representing those ONNX computations and doing an implementation of the ONNX API within a zk virtual machine. right? So there's many zk virtual machines that we're building, whether it's zk VMs or some other non-EVM machines. So one such approach is the one that Giza is taking, which they're just implementing the ONNX runtime format within Cairo, which is the language that proofs on the Starknet Cairo VM. So they have this virtual machine which you can create Stark proofs of, and they're implementing ONNX within the Cairo language. Another approach that some other folks are taking is sort of more bare bones, which is actually writing or deriving a variant of a proof system that's more oriented towards machine learning operations. So in the world of machine learning, we're usually dealing with floating point arithmetic, as opposed to in the world of zk, where we're usually doing with field elements, and field elements don't necessarily don't represent floating point numbers very well. You need to do this sort of step that's called quantization, where you're representing floating points using field elements, and that operation is very slow, and it takes like a lot of computational complexity, and therefore it's not very performant. So what they're trying to do is more like, let me try and see where the cryptography theory is, and whether I can use some different variations of different proof systems to sort of cater more to this floating point arithmetic side of things. And there's also other approaches, like, for example, the RISC-0 approach. RISC-0 is a project that's creating a prover of the RISC-V machine. So this would be similar to the proving ONNX runtime on a zk VM. In this case, you're not necessarily proving ONNX. You can just implement any machine learning algorithm on RISC-V, and then just prove that using RISC-0. That would be one approach. Another more painful one would be handwriting zk circuits. There are some people that have tried to write circuits for some machine learning operations using zircon and some other frameworks, but this is also viable, although albeit a lot harder, and also harder to prove security. And even some alternatives to zkML altogether, using sort of the optimistic approach, where you're doing some bisection games over the execution trace of some machine learning model. So I'm going to sort of show a little bit of a demo of each of these different approaches. So one of this is the zconduit approach. So this is just a video taken from their repo, which you can scan the QR code for on the left. I don't know if this is readable on the screen. Can you see what's written on there? More or less. Yeah, it's the TLDR is what it's doing is it's you download the. Okay. Interesting. That's good. Yeah, I'll talk over it a little bit before I do it. So you just download the zkL CLI tool, which is written in Rust. You build it using Cargo, which is the package manager for Rust. Once you have a binary, you just do ezkL. You can either import a model that you've already created using PyTorch or some other tool. And as long as all of the operations in your model are part of the ONNX API, and all of those specific operations are supported by ezkL, what you can do is you can, for example, generate some test parameters, which is also part of this demo. You then put your ONNX file into ezkL, and you create a circuit representation out of it. Let me just play it from the beginning. Maybe if I can full screen it. All right, so here, what it's doing is it creates a table representation of the ONNX model. So it shows you all the operations you're doing. So here you have matrix multiplications, ReLU, and some other operations. Then you generate some input parameters. And then you feed essentially this circuit that you generate using ezkL. So it's a Halo 2 circuit representing this machine learning model. And you're feeding it some inputs, and you're creating a proof out of a Halo 2 proof, a standard Halo 2 proof. And another cool thing that ezkL does is that it creates an EVM contract, a solidity contract for the verifier. So if you want to, for example, bring those computations on chain, you can, right? You just create a verifier, you deploy it, you then run a proof of some machine learning model inference, and you can verify the proof on the EVM. So this is one approach. Another, okay, this bugged a little bit. Slide to show. All right, there we go. Another approach is the one that Giza has, which is just write some Cairo, right? Cairo is a DSL that targets the Cairo virtual machine that runs on StarkNet. Cairo, you can also run it off-chain, right? You don't necessarily need to run it inside of the on-chain VM. You can fully just download a prover locally and just run a proof locally and verify it locally as well. So Cairo is essentially like a variation of, they're building it using some Rust tooling. So you can use most of the Rust tools that you're used to, and it's a variation of Rust, right? So you see like the syntax is fairly similar. It's just like some more constrained version of Rust, where you have traits, you have the borrow checker, all the goods of the Rust ecosystem, right? So you're essentially just writing a Rust program or a Rust-looking program using Cairo, and then you compile it to a Stark, and you can verify that Stark either locally or on StarkNet if you deploy a verifier contract on StarkNet. So this is their approach, and essentially what they've done, the link that I show is Orion, which is sort of their system in which they're implementing every single operation inside of the ONNX runtime using Cairo, right? So all the operations like adding or subtracting or ReLU, like standard operations that you're doing inside of ML models, they're all implemented using Cairo. And the third one, which is a sort of more like bottoms-up approach, is what Modulus Labs is doing, where they're building this variation off of the GKR proof system that is called Remainder. And this proof system is sort of more tailored towards these machine learning operations so that they would be cheaper if you actually then write a prover using this proof system. So one interesting aspect of this is that we at Worldcoin, we're doing various different things, one of which is a privacy-preserving proof of personhood protocol. And this protocol, essentially, the way that you verify personhood in this case is a hardware device. This hardware device, you can think of it as an iris imaging device. The thing that it does is two things. One is to prove that a person is real, right? So it's not like some image, or it's not some person like wearing contact lenses or glasses, like some way to tamper with the iris. And the second thing is once you take an image of the iris, you represent it, or you represent the randomness that is encoded inside of the iris, and you're checking this randomness against a set of all the other people that have signed up, which also have some randomness encoded in their iris, and you verify that they're unique. So one of these steps, it's called iris code generation. So you have an image, normalized image of an iris, and from there you're sort of trying to do a vector representation of it, and then you're doing a distance check of vectors. So that's how you determine uniqueness. And currently, all of that is done within the hardware device. And so if you ever update the machine learning computation that generates this vector representation, or a creation of an embedding in more formal terms, this needs to always be done at an orb, right? So if we ever update the way for generating these iris codes or these representations of randomness, the user would have to go to this hardware device in person again, which is not ideal. So what we're doing is that we're trying to create a zk prover that will allow you to create a proof of the computation in which you're going from this image of an iris, which would be self-hosted by a user on their phone, encrypted using a key on their secure enclave, for example. And then they would be able to download a new model alongside with its prover, and they would be able to create a proof locally on device that their iris code was generated correctly, their representation was created correctly, and then just upload this representation onto a backend, which would verify the proof. And then the user would be inserted into the Merkle tree of registered users on a smart contract, which is called World ID. So what we're doing with Modulus is that they're sort of building a circuit in their remainder proof system that will allow you to do this. The reason why we're choosing them and not the other approaches is that we're expecting to run these proofs on mobile phones. And like 32-bit Android phones don't really have a lot of computational power. So Halo 2 or the Stark prover, like they're already too big in terms of memory consumption. So the reason why they're going also with GKR is that it's a streaming proof system, right? So you're able to bottleneck or cap the memory consumption that they have. So you can cap it to some like acceptable threshold of RAM on the mobile phone and generate these proofs in a sort of more like albeit slower, it's permissive because the memory constraints are not too high for the prover. So yeah, they have a paper for remainder coming fairly soon. So everybody will be able to check it out. And they're sort of taking more like the experimenting at the lower levels of the stack approach versus others that are trying to do like more production right now. Like I have a compiler, I can create a proof, I can run an OVM, etc. So use cases. So it's a good meme. I'm in the arena trying stuff. zkML is below my line. So use cases, right? So why would we want to do zkML in the first place? So there's a few, one of which is just, there's many machine learning as a service providers, right? So let's say I have an API. I want ChatGPT to give me the answer to a question I give it. How do I know that OpenAI is actually running the ChatGPT I'm paying for? Let's say that there's different variations, right? Like there's GPT-4, there's GPT 3.5, maybe there's a new version, GPT-5. How do I actually know that their website is actually using the model that they say they are, and not using just some other cheaper version to run on infrastructure and just charging me more and purchase and like pocketing the difference in the cost, right? So one thing that they could do is that a user could request a zero-knowledge proof of this inference, and I would be able as a user to verify that, okay, they're using the model that they say they are, and they can, for example, like hide the weights, just publish a hash, and everybody can commit to this hash, right? So I'm using the hash of this model, and you can prove that every user is using this model, although it might be hidden because it's something that might be intellectual property of some company. But they can at least prove that every single user is using this specific model. Nobody's getting lied to. And maybe in a few years, once the model is deprecated, they can actually reveal the model, and you can check that, okay, this was the hash of the model that I was using. Another one is just bringing machine learning on-chain, right? Machine learning is usually something that is very computationally expensive. Therefore, in a prohibitive environment, such as let's say the EVM, Ethereum, there's only 30 million gas in each block. I would run out of gas fairly quickly. So there's no possibility that I would be able to do machine learning operations there. So if I want to build an app that leverages ML for, let's say, prediction of something or classifying of something, then I would not be able to. So if you have this approach where you just do a proof off-chain and deploy a verifier on-chain, I can just submit this proof, excuse me, and I'll be able to verify that this ML computation happened. It's essentially like what the rollups are doing. Rollups are proving some computation off-chain, bringing a proof, and therefore everybody's happy. Another one is anomaly detection or fraud prevention. So there's a class of machine learning algorithms which are called anomaly detectors, right? They're fed lots and lots of data, and they're able to detect some anomaly. In the context of blockchains, this is really useful because we have lots of financial operations, right? We're able to sort of feed it lots and lots of historical data of transactions, let's say on a DeFi protocol. And if there's one that seems really weird, we can flag it to the protocol. Let's say that they somehow tweaked oracles and they're able to like trade according to some like weird price setting. So we would be able to detect this and submit a proof to the contract. You would be able to freeze it or do some logic based off this. This would be useful. On fraud prevention altogether, this is not necessarily zkML, this is just zk in general. If I'm able to prove to a contract that I'm able to take it to a state which breaks some invariance, right? You can formally specify some invariance in a protocol that cannot be broken. And if I prove to the protocol that, hey, I broke your invariant, just stop it, freeze it, or leave up to governance like what to do next. Another one is decentralized Kaggle. So Kaggle is a machine learning platform in which there's people submitting competitions for different machine learning problems. And the people that are competing are submitting solutions. And once the time period for a competition ends, the person that submits the best solution gets the price for the competition. And there is an intermediary, in this case, Kaggle, the platform, which sort of does has all the trust, right? Like the person submitting the competition puts some price, the Kaggle gives the price to the person that has the solution, and the person that has the solution has to publish the solution to the person that posted the competition. So in this case, we can get rid of the intermediary just by using zk proofs, right? If I'm able to prove that my model has the highest accuracy on some public test data, I'm able to prove that I ran my model inside of a zk circuit, and hey, like it has more accuracy than anybody else. So I can claim the price atomically and then automatically reveal my weights if I commit to them. Yep, so that's one. Another one is just inference on private and sensitive data. In this case, the prover would always have access to the private and sensitive data. Otherwise, they would not be able to create the proof. However, if you want to hide some sensitive data from, let's say, some third party, you'd be able to hide, like in the case of the verifier, some data from the verifier. This can be good for like medical data or some other particular use cases. The third use case, in the case of Worldcoin, I already mentioned, is this iris code representation. If you want to read more, I really recommend you go to whitepaper.worldcoin.org. We have like more in-depth explainers that I don't really have time to go into here. And one last one, which is a buzzword that many people in the blockchain crypto space have been throwing around lately, which is intents. Intents or intent-driven sort of thinking about virtual machines. Essentially, what you do is that I, as a user, can declare some parameters of my transaction. For example, if I want to do a swap on Uniswap, I can declare that I want to do a swap if and only if the price of ETH is more than some threshold, let's say 2,000, right? And I want a slippage that is no higher than 2% or 1%. So instead of me having to wait until that's actually the case, I can just cryptographically attest to a transaction. I can do a signature on these parameters. And there's a builder or a proposer that essentially builds this transaction. And as long as they satisfy my conditions, this transaction gets executed. And the builder essentially gets the rewards that I post for doing this service for me. This is sort of like a new paradigm that people are thinking of in terms of programming blockchains and how users will interface with them. I'm sure you've heard of things like account abstraction and many other things that pertain to intents. I really recommend checking out Uma's talk from Research Day back in New York, and there's many talks that are going over in Stanford at SBC. There's lots of talks about this, but in the context of zkML, where intents would come into play is that if I have let's say that I have a DeFi protocol, let's say like Yearn, right? I have a yield aggregator. I am sort of trying to maximize the yield of some assets that I put into this protocol by routing these assets across different protocols. Some of these yield strategies, as they're called, are fairly sophisticated, but in the context of blockchains, they always have to be deterministic in the program that you're running on top of the blockchain. You often have very little off-chain logic. So what you can do with zkML is that I can define a strategy that predicts where the highest yield is going to be using some sophisticated model. And I can prove to Yearn that I'm actually using this model that everybody is trusting and route the protocol to where the model is predicting the highest yield. And I can actually submit proofs and, hey, this model is predicted, hey, if I put it here, it's going to have a higher yield. So this is where something like zkML would be useful, right? I'm able to create a zero-knowledge proof that this model predicted some higher yield somewhere. So this is sort of like one of the use cases where zkML would be useful in the context of intents. So where to learn more? So I put together one resource, which is called Awesome zkML. It's just a GitHub README where you can check out different resources like blog posts, articles, code bases, papers, etc., that are related to zkML. And another one is an article spotlight. So every time I give a talk about zkML, I usually put some article that I like about zkML that goes more into depth. So if you want to read some more after this, then I definitely suggest that. Awesome. So that was my talk. If anyone has any questions, feel free to ask. I'm happy to answer them.